So our next speaker, the last talk of the session, is given by Ike. Who's going to talk about the unification for subformula linking under quantifiers. Please.
Yeah, thanks. So I will talk about subformula linking, but kind of the general setting or the general problem we're dealing with is that, well, I think that formal proofs are simply too hard to construct. I mean, it's a fun puzzle, but sometimes you just have to jump through too many hoops to get what you wish to do. So let's look at an example. So say you have some predicate P and Q, and you have a witness for P. You're trying to prove a witness for Q, and additionally, you know that every witness for P gives you some witness for Q. Now, if you look at this, one of my first intuitions would be, hey, the only way to get a witness for Q is by using this hypothesis. But then when you think about this a bit more, you will notice that you cannot directly use this. You will need to first take apart the witness you have for P, then say this is my witness, and then apply the hypothesis you have. But wouldn't it be great if we could actually directly use this intuition we have for using these matching Qs? And not just in this easy example, but also in more complicated examples where we have more quantifiers, maybe conjunctions and disjunctions flying around. So this is what's known as subformula linking. And there's some recent work on this in CADE in 2021, and also in CPP 2 years ago, the ACTEMA system and the PROFINT system. And in these systems, you have a graphical interface where you can say, hey, I notice I have this predicate here, and in my hypothesis, and here in my goal, these match up, so think of an easier goal which I can then prove. So the setup is as follows. You have some context with a bunch of hypotheses. You have the thing you wish to prove, G. As a user, you point out the hypothesis you think is relevant, and specifically also an atom that occurs in this formula that you want to use to prove your goal. Now, after you point this out, the user or the system will automatically determine a simplification O, for which it holds that together with your hypothesis, this implies your goal G. And then you will continue by proving this O, which is hopefully easier. So specifically on the example I showed you before, after pointing out and noticing, hey, there's these two Qs here, the system will say, okay, it's enough to prove there exists a Y, Py. This will match up with the thing you had before. Now, I've been talking about this for a while, but I'm in the separation logic slot, so you must be thinking, where are the separating conjunctions? So subformula linking is also something that is useful in the separation logic setting. So here's an example goal you might encounter when using IRIS, the framework for concurrent separation logic. You have a predicate P and resources Q and R, and you notice, hey, this R occurs both in my hypothesis, but also in my goal. And you have this iframe tactic, which also sees that and uses it to cancel them out. So you are presented after this iframe tactic with an easier goal with this R removed. And notice that this also works even with R under the existential quantification. However, if in a slightly different situation where you, instead of this working for all A, you have a witness for the predicate P. If you then try to use iframe, it doesn't work. So iframe does some subformula linking, but it cannot do the more complicated things that these ACTEMA and PROFINT systems do. So iframe cannot instantiate these existential quantifiers, but these existing systems for specifically subformula linking are able to do such things. So maybe we can use their ideas to improve the situation. Now, there's another place where subformula linking occurs in separation logic, and that is in diaphragm. So diaphragm is a proof automation library I develop for IRIS, and the main driver behind its proof automation is also subformula linking. So diaphragm is specifically targeted for the verification of some fine-grained concurrent data structures. And during the verification of a reader's writer look, I ran into a problem. So there's a bunch of quantifiers there as well, and diaphragm does something, but I kind of got stuck, and there was a goal that I didn't expect. It was the quantifiers gave troubles. So this problem is actually a subformula linking problem just for the quantifiers. The separation logic business there is not the hard part, it's the quantifiers. So I thought maybe these existing subformula linking systems could figure out a proper way to continue. So I distilled it down, and I will show you the tricky example. So suppose we want to prove that there is some person that is born on the last day of some year. This is our goal. We are given the following hypothesis, namely that for all the days in the recent past, some person was born on that day. Now the question is, what is the easiest goal you can come up with that would suffice to finish this proof? So if you think about that for a while, hopefully you'll come up with, there exists a year such that the last day of that year is in the recent past. So if you take this apart, plug it into the hypothesis, you get indeed a person born on the last day of some year. Now, what do the existing systems for subformula linking say? Actima simply says, tactic not applicable, I can't do this. And Profint, the other system, does something which is arguably worse. It gives you some simplification, which has the correct shape, but also has this red highlighted part where it says, yeah, all people should be equal to some person, which is not what you want. So for the rest of this talk, I will try to come up with a solution and try to tell you how we can compute these simplifications. Right, so central to computing these subformula linkings is the following judgment. So H is our hypothesis, G is our goal, and O is the simplification we want to compute. And it's defined simply like H and O together give G. So H and G can be any formula in intuitionistic logic, and so we have rules for the various shapes they have. I will show you two of these rules on this slide. So the first rule is when the hypothesis is an implication. What we will do is, okay, we will try to see if the right-hand side of this implication can give us our goal. So supposing we find some simplification O so that H and O together give G, then the implication together with L, we need L to get H, L, so that after this, both L and O with the hypothesis we have together give G. So that's one rule. The other rule I want to show you is when the goal is a disjunction. So if we're trying to prove G1 or G2, what we can then do is try to see if we can find a link between H and G1. Now, if we do, it's enough to prove O, but if that for some reason turns out to be hard, we can still also prove G2. So we have these two rules. Now imagine a situation where your hypothesis is an implication and your goal is a disjunction. Now both of them are applicable, and so the order in which you apply these rules matter. So this is already one thing that is hard about computing these simplifications. Now let's get to the quantifier rules. So if our hypothesis is for all quantifier, or our goal is an existential quantifier, one rule says, okay, let us try to find a simplification that works for all x. So you get some O out of this. Now O may mention this variable x. Note that G does not mention x, since it's bound in H. Okay, so if this is the case, then it's enough to find some x for which O holds. If we get that, then we can plug this same x into our hypothesis for all xh, and then our premise indeed says, okay, now we can get our goal. Now, these rules I've showed you just thus far are the basis of the profint system. They add the following base rule. So if you have atomic predicates Q on both the hypothesis and the goal side, then profint says, okay, it's now enough to prove these two values equal. And this works, of course. It's a sound rule, but it's often not what you want. You very quickly get scoping issues. So you can imagine that these x and y come from different quantifiers and that these can actually not touch. You can also imagine x and y being two totally distinct values, and then you don't want to prove that these two are equal because they're obviously not. So that's the profint approach, and I think it's not the right one. So Actima takes a different tack. Actima says, instead of equality, we require these things to be exactly syntactically equal. And it will use unification to deal with existentials. So this works, but you need two additional rules for the quantifiers we saw before. So when the left-hand side is a for all quantified hypothesis, or the right-hand side is an existentially quantified goal, we need to be able to plug in a specific value for this for all xh. So indeed, that's what these rules say. If we plug in a specific value t, and then can find some o, then this is also a valid simplification for all xh. Now, of course, when you're actually running this simplification, when you're building this proof, you won't know this t beforehand. So in the implementation, this t will be an EVAR. But as soon as you apply the base rule, this will unify the EVAR t with a concrete value. So let's see how that works on an example. So this is the example I showed you on the first slide. We want to prove exists y qy, and we know that for all x, bx gives qx. Let's start by applying the rule for the goal. So the rule for when the goal is an existentially quantified formula. And we'll use the rule that says we're going to find a link for all y, since in this case that's valid. Now the next thing is a rule for the hypothesis, since the goal is now an atom. And in this case, we want to plug in, we can see beforehand that we will want to plug in the value y. But in the implementation, you will plug in an EVAR and hope this gets unified to something nice. So that's what we'll do. So we will get now that our hypothesis is P applied to some EVAR T implies Q for some EVAR T. Now then we apply the rule for when the hypothesis is an implication, which says, okay, we need to prove P EVAR T and whatever the simplification will be for the topmost premise. And at this point, both the hypothesis and goal are atoms, and we can apply the base rule, which will then unify this EVAR with y everywhere. The simplification is just top, and this propagates down in this proof tree, so that indeed, at the end, we get exists y, py, and top. So this and top thing can be simplified away, but I will not discuss this. Now, this means we have two rules for when either the goal is an existential quantification or the premise is a for all quantification. We can either instantiate it with a concrete t, or we can quantify. And this turns out to be not always enough. So in the example, the tricky example, where we have for all days in recent past, there's a person born on this day, you will notice that first we need to choose which rules we will apply first. So if you've done some of these intuitionistic logic proofs, you know that you first need to destruct the existential in the hypothesis before you can instantiate the witness. So we need to prioritize the hypothesis rules. This means we need to choose a rule for this for all D. So in the Actima system, we need to choose instantiate or quantify. Now this link will not work out if we quantify, since the person will get on that day. It doesn't work for all days. We want specifically the last day of some year. So we will need to instantiate. And if we do that, we will instantiate D with the last day of some year. We don't know which year. But remember that the simplification we want to compute should existentially quantify over this year. So somehow we need to have this EVAR now, EVAR year, but we want an existential quantifier. So how do we turn this EVAR back into a quantification? You can't if you tried this. But maybe we actually can. So what we need to make this work is the following. We first need a rule that can both quantify and instantiate. Of course, we still want to leverage the unification business that Actima does, but just in a slightly different way. So when D gets instantiated with some EVAR, last day of EVAR year, then we want to detect this and quantify over this year to make this still as simple or as general as possible. So yeah, we want to turn EVARs back into quantifiers. And these two conditions can actually met the contribution of this work. We can quantify on the instantiated. So this is a subformula linking system that generalizes what Actima does and can actually compute a valid simplification for the example. So let's first look at that rule. So it looks like this. What are we doing here? We have a list of quantified variables y, so we're quantifying, and we have this t, which we're instantiating h with. Let's see how this relates to the existing rules we saw before. So the instantiation rule of Actima follows from this rule by just taking the list to be empty. It's a direct application of the rule. And the quantify rule also follows by taking the list of quantified variables to be just x and also instantiating with x. But it's strictly more general than that. Now you might wonder, okay, sure, you have this rule. How do you determine what to quantify over and what to instantiate with? And this is indeed somewhat tricky. But first, let's write this down in Coq to see what it would look like. So in Coq, it looks like this. So now we need to make, we have y, big Y a type. This is what we're quantifying over. We have t, the thing we're instantiating with, but now we have an explicit dependency on this little y, and the same for O. When we're applying this rule, when we're finding a simplification, we don't know upfront what this big Y will be, what little t will be, and what big O will be. These will all be EVARs. Now we want Coq to, when we're running this algorithm, to fill in the appropriate argument to h. And Coq will not be very happy to unify this EVAR t applied to y with just anything, especially since the type of this little y is also an EVAR. So the solution to this is, of course, use even more EVARs. So what we're doing here is we're replacing this ty and oy we saw on the previous slide with new EVARs, O prime and A prime. But for these existentially quantified O prime and A prime, little y is in scope. So that means we can first run this algorithm for finding a link. this will possibly instantiate A prime with something specific. Then, when we're proving these equalities, what we can do is find all the evars that occur in this term. What we will then do is, okay, we look at the types of this and say, well, big Y, which is still an evar, a type, that's just going to be the product of all the types of these evars. And then we can say, well, these evars are then just projections of little y. So we're kind of saying, oh yeah, all those evars you found, we were quantifying on them all along, retroactively making the right quantification. Yeah, so that's this work, and specifically on the tricky example I showed you before, we can compute the correct simplification. We can also, in the paper, we have formally shown that it kind of lies between the Actama system, which cannot determine this, and the Profint system, which can determine even more links, but sometimes determines or finds links you don't want. Now, getting back to iframe, which I mentioned at the beginning, iframe was not able to, or is not able to, instantiate existential quantifiers, for example, here. But the techniques we developed in this paper can be used to improve iframe to make that happen. So there is an open merge request about improving iframe, which I hope to merge one of these days. So if this is something you would appreciate, please let us know. Yeah, thanks.
Thank you. Questions?
I have a question about whether this problem will still show up if we imagined a small change to the type theory that you're working in. Specifically, it could still be constructive logic, but we don't try to have a distinction between prop and set, in which case I think it's easy to eliminate all the existential quantifiers in hypotheses by replacing them with Skolem functions. If that happens, do we need this kind of machinery, or would something like eauto just do the right thing?
Thank you for your question. So I guess that indeed, if by this columnization you have all the existential witnesses beforehand, then indeed that might not be an issue. But in the systems, or at least in Iris, this is not the case. You have a bunch of existential witnesses which you cannot know beforehand. So there it is very much a problem, I would say.
It would be interesting to think about how we could maybe change the foundations that Iris and other libraries are built on, or is there some fundamental reason that would break something else?
Yeah.
Thanks.
I guess it's possible to imagine that a system like this could be led astray by hypotheses above the line that seem relevant but aren't useful. So what happens to all of these systems in such a case?
So in the Actama and Profint system, this is still driven by the user saying you need to use this hypothesis to the goal. So in that case, if the user makes a mistake clicking the wrong guy, which seems applicable but really should not be used, then I would say that's the user's problem. For diaphragm, which kind of does this, it looks, hey, I need to prove this predicate now. There's this hypothesis which seems applicable, so let's just use it. There, the problem hasn't popped up very much at all. And I think this is mostly due to being in separation logic. So if you're looking for a points to connective, and you have a way to find one, probably it's the only way to find it, and it's not much of a problem there. But in general, intuitionistic logic, I would say, yeah, this is gonna not always be the right thing to do whenever you see it.
Other questions? Just to build up on what Andrew was saying. That in using iframe, my personal experience is that sometimes just the iframe of iris, not diaphragm, it picks the wrong things, and you have to say that specifically I want to frame this a specific thing. I can imagine that with your work also, if you try to automatically find a witness, then you might find the wrong thing, right? There might be multiple things of that type in the context.
Yeah.
So have you thought about a way of specifying that I want to use this specific hypothesis, or
Not
how do you handle
much more, no. I guess iframe already has the way to say, I want to frame this thing, but there's also the part where you want to frame it in a particular place in your goal. I have not thought about how to indicate that. No, sorry.
Thank you.